What I'm going to talk about today is I'm going to try to convince you that when you're building your next new database, and I'm going to do this by an example, specifically InfluxDB 3.0, that you aren't going to build it from the ground up like people have done before. Instead, you're going to do it by building it out of reusable components. It's not a terrible idea. And so to do that, I'm going to try to talk through basically three things. I'm going to talk through at a high level what the database implementation trends are. So this is high level stuff, right? And I got to give you enough introduction about time series to explain why we're doing this. But then I'm going to try to spend as much possible time going down into the technical stuff, right? Like I'm a database developer, so if you turn me loose, I'm just going to sit here and talk about database internals the whole time. But I'm going to at least give you like 15 minutes of not doing that. So, oh yeah, you can read all about this in the blog. So the longer term trend in database, the database industry, if you haven't been around or haven't watched, is it went from a few relatively monolithic systems like Oracle, DB2, they're still doing great, but I spent 5 minutes on the internet one day, right, gathering database images, and it's crazy, right? Like, and there's just like a new database every time. Go search like new database on Hacker News sometime, and it's overwhelming. It doesn't matter where you go, and I think the trend's only going to continue. And so I think what's driving this trend is that it was predicted by most things in the database industry by Mike Stonebreaker 20 years ago, where the basic observation is if you, rather than having one general purpose system, if you spend a bunch of time and you build a system optimized for a particular workload, you can get a 10x performance improvement. And that 10x, approximately 10x order of magnitude performance improvement justifies building a new system. So that's basically what Influx did, right? What time series databases did in general. So I'm going to try to, so I'm going to walk you through our journey of doing this again. But also why we used a bunch of open source technologies to make it happen. So to understand sort of time series databases in general, you have to understand they're different than, like why are they different? Why is there even this category? Obviously, given the name, they're for storing time series data, but they have interesting technical properties. Specifically, they have high volume denormalized ingest, so that basically means you get like reams and reams of CSV files in the equivalent of CSV. It's not quite CSV, but it's close. It's called, in Influx's case, it's called line protocol, but it's basically semi-structured CSV, and it's a huge amount of repetition. And the goal, typically in time series use cases, at least for the ones that time series databases specialize on, is you got to get that data queryable as fast as you can, like measured in tens or hundreds of milliseconds at most. Also, different than a classic relational database is it has schema on write. That doesn't mean it doesn't have schema. It means that you don't specify the columns up front. So as the data comes in, you can add new columns anytime, but you don't know them up front. And then you also, like most things, right, you have this rapid value decay where the data from last 5 minutes was probably much, much more important than the data from 3 years ago. That doesn't mean the data from 3 years ago isn't valuable, but the decay falls off quickly. And so you really can't afford to keep your 3-year-old data on the same storage tier as your really hot, really important stuff. So there's like, I could fill like slides with examples. It turns out it's a very important use case. There's a whole bunch of systems that do this both open and closed source. So why do we need another one, right? That's basically the question. Of course, we need another one, just like that chart shows. So specifically, when Paul Dix, who's the co-founder of Influx, was looking around, he had a great 1x product, but there were a couple of limitations he wanted to work on in his next version. The first one was there was a notion, traditionally how they're implemented. I'm sorry I had to do database weenie stuff. Is like traditional architecture of a time series database is effectively a key value store. And what you need to do is you'll be able to map the series that you're storing into the key value store, and then the values that you query are basically a contiguous range. So if you do that, that's great, except if you have a large number of series that you can't map to a contiguous range in your key value store, you're screwed. So he wanted to turn it into a column store. He wanted to use column store technology. He needs infinite retention, so that basically means you have to have a split tiered storage system, so you can't spend a lot of time, or you have to be able to store data both on hot storage, like expensive, fast storage, but then also transition it to slow storage. As you probably could guess, that means object store in this day and age, right? So you need a system that has disaggregated storage. You need elastic scalability, so you can throw more compute at it if you want more system. But like classic databases, InfluxDB 1x included, are basically what are called like shared nothings, have a shared nothing architecture. It's actually also what Vertica had, which basically means you tightly bind the compute to the storage. And so if you ever want to scale the compute up, you have a real problem because you end up having to shuffle the data around. And also ecosystem compatibility, right? Influx is great, has a language called InfluxQL, has a special thing, but if you now want to go connect it to the rest of the ecosystem, as much as you might love to complain about SQL, and having basically implemented SQL databases for 20 years, I'm with you, it's terrible. But it's like, it's everywhere, right? It's everywhere in the ecosystem. And so if you want integration of the ecosystem without a huge investment of connectors everywhere, like you basically have to play in that ecosystem. So we wanted to be able to do InfluxQL and JDBC and SQL and all that sort of stuff. All right, so that's basically the requirements. Let's move through, right? So let's build the new database. This is Paul, right? Like you gotta understand what Paul. So the first thing is, it's actually very expensive to build a new database. I spent a few minutes on Crunchbase a while ago. These are probably out of date by now, but it's basically over $100 million, right, for any reasonable data. Influx, by the way, is the same basic order of magnitude. I did this at Vertica too. Obviously, not all this money goes to engineering, but a significant amount does. So the point is, if you want to build a new database engine, right, especially one that's totally vertically integrated, it's a very significant engineering investment. So I know this meme has also been overused, but I still find it super, super relevant. So that, like, this is Paul, right? If you ever know Paul, this is classic him. He's Buzz Lightyear. We're going to do this thing. And Evan, the CEO, is like, well, how are we going to pay for it, right? We don't have another $100 million in the bank. So Paul wrote this blog, and like, you can go read this. Like, he's one of the visionaries Julian was just talking about, where he basically sees in advance where things are headed. And so he wrote this blog post in 2020. You probably can't read that on this slide. That basically says, look, you use a collection of these open source technologies like Arrow and Parquet and Flight and their ecosystems. You can build one of these systems, build a new database with much less engineering effort. So that's what we did. And so now I'm going to switch to like the really database weenie talk, if I haven't already done that for you. And we're going to go through each one of these sort of technologies and explain what we used them for in Influx, what we got out of it, and sort of what in like a high-level overview of what they are. So in particular for file, like this, I'd say a selection, a fine selection of the types of things you need for a database. So you need a file format, right? We chose Parquet. I'll explain why. You need column memory representation. I'm not going to put another coin in the jar, but it was Arrow, right? I think the other thing that was important is like you have to actually have operations to operate on that data, which we also, it's kind of Arrow, but we use the Arrow compute kernels. I'll talk about that in a little bit. You need a way to run SQL and queries, so we use DataFusion for that. You need a way to like transfer the data over the network. Like, it's not sexy stuff, right? Like, people have been doing this for many years, but like it needs to be fast, and you don't want to re-implement it. I know I've done. It's like. And then, of course, you need also JDBC and ODBC drivers and like the connectivity to the rest of the ecosystem, which also is a giant lift. We use Arrow Flight SQL for that. And so now what I'm going to do is go through each one of those technologies and explain what they are at a high level. So I hope you're ready. Oh yeah, this is our architecture. I'm not really going to talk about this one too much because I'm going to go into detail more. But it's basically a disaggregated system. It looks like basically if you're building a database now, what you would expect is that it is formed of multiple different services. The core tier is on object store, and then it's got different services that do different things. So that's basically the architecture. Here's the marketing slide that basically says we achieved the goals. We can talk about that, but that's compared to the other one. What I want to do is I want to spend most of the time talking about the specific technologies. Before I launch into it, though, I need to say they're basically all Apache project, and I wanted to spend a few moments explaining why I thought Apache, why it's so good. I mean, maybe you got too much of it with Julian already, but basically the core benefit for Influx, from my perspective, it's different. This is not some other company's product, right? This is, if you build your product on top of open source technologies, you want to have like confidence that the open source technology is not going to move around or change. So in particular, Apache basically, so that's the core benefit, right? You get this predictable foundation. I checked the other day, the Apache software license hasn't changed in 20 years. Right? That's like forever in tech industry. And it has like low risk of changes. But even in like the last few weeks or months, you've seen major announcements from other vendors with like license changes on open source products like Redis, for example, and whatever OpenTofu called. But you can see it as the business climate changes, the license might too. Apache, that's not a problem. Julian talked a lot about community and communication building. All Apache projects have like all the communication is open. It sounds really boring, right? It's like it doesn't mean it's simple or it's easy to understand what's going on, but it's all there. So if you want to, you can. And the other thing has been extraordinarily valuable in attracting multiple vendor participation. I wish Paul was like, he would talk a lot about it's fine to have multiple vendors contributing back, right? Because now, even if they're your competitors, if they contribute back to the same open source project, it brings you all forward. And it's been extraordinarily good at doing that. The other thing is that it actually lowers the long-term maintenance risk. So like, if you build your product on top of an open source project that has like one brilliant committer, or it has a company that's backing it, right? Like then now you're subject to that particular committer's like personal life, right? Maybe they have a child, maybe they move off, do something else. You don't really know, and it's hard to predict. The fact that Apache focuses on the community means that you're basically have a much better chance of surviving that kind of event. Or curve shift, or like whatever we're going to be talking about next year in the VC funding cycle that's non-generative AI, which happens. So, all right, here we go. Parquet, here we go. I think Julian just talked about it. I'm going to basically do all these slides with what we get out of it, then I'll tell you briefly what it is, and then I'll explain how we use it in InfluxDB 3.0. So the core thing I think that you probably got is Apache Parquet has basically the features that I guarantee you will basically end up re-implementing if you do your own file format and you have a columnar store. And so by using it at the beginning, you basically save yourself that engineering effort, right? It sounds really simple, but I'll try to convince you some of the features that you probably rediscover that you need. So the first thing is the compression. There's actually a lot of the early time series databases actually have their own specialized file format because they say they need it for specialized compression. And it makes a lot of sense, right? Like if you have a specialized use case like time series, you can take advantage of the patterns in there. But actually it turns out Parquet compression is very good. It's actually, I'll show you in a second, did better than the TSM file format. There's also a whole bunch of techniques that you need to implement fast query execution against your files, which again, I'll also explain. But Parquet just has it already, right? And the open source readers know how to do it. And now it's also basically become the de facto interchange format. So you write Parquet files, especially you write Parquet files to object store, if any of you have been paying attention to the other talks today, right? You now effectively can be used by a huge variety of tools. So Parquet is a file format. It's hard to beat. Lots of people, like, we can talk over beer like all the problems with Parquet, but those features are pretty compelling. So let's talk about it. First thing, I told you compression was good. So the first, like I said, like if you read a lot of papers, especially the ones about specialized time series databases, they'll often talk about their special file format and how awesome it is, and they take advantage of the fact that the timestamps are like relatively small differences between them or whatever. So we did a comparison early on when we were doing InfluxDB 3.0 to like basically, would it be okay to use Parquet, or do we have to do something special? It actually turns out Parquet is basically really, really good. Right? So the original TSM file format, this is for some internal file, some internal format, it's like 600 gigabytes approximately of TSM data. To give you a sense, if you just gzip that, right, it goes down to 97. But with Parquet, it's at 120. Now the problem with the problem with gzip is you can't query it. Right? So with Parquet, you basically get almost as good compression, but you can also query it really fast. Right, and that's with a file format that's supposed to be really good for time series, right? So like that was pretty compelling result. And this other chart basically shows the same result. You don't always get 20% compression. Sometimes it was more like 10%, sometimes more like 18. But by and large, basically any data set we tried, we got dramatic. And this is one of the ways you get that like 45x better compression or whatever, is with this. 45x better storage cost, I think. All right, so getting a little weenie here. I want to explain this. So at a high level, Parquet is organized in these things called row groups. So what that means is if you're storing tabular data, right, like you have a table, right, with rows and columns. I know that's old school. By the way, Parquet can also do structured data, but we don't use that yet in Influx. So you have tabular data. What actually it means is you take horizontal strips of that, right, like chunks of the rows, and that gets encoded. So yes, it's a columnar format, but it doesn't actually encode the entire columns together. It actually breaks them up first into horizontal strips. And I'll explain why this is important in a second. And so you have multiple row groups in the file. And then within each row group, the columns are encoded. So, oh, by the way, yes, speaking of not reinventing, like this is not something Parquet came up with, right? This is actually known as PAX, if you, again, read database literature, right? Like this has been around for a long time. It came out of the database research world. And I've read blogs, which I won't name, that basically talk about the great new innovation in their file format, and they're basically describing implementing something like this, right? So like they had to go through the hard trouble of rediscovering why this is good rather than just using Parquet. So you should use Parquet, basically, is the conclusion. Now, the actual structure of the files looks like this. You have encoded the highly encoded blocks are basically appended one to another inside the file format, and then it's got a footer at the bottom, which is very important. So this footer contains information about where to find inside the file the blocks that make up both columns and rows and row groups. And what's in there is very, very important. So it has min-max counts, nulls, and it lets you very quickly basically avoid looking at most of the file for selected predicates. Again, this is also not something that Parquet invented. If you want to read up on it, it's called zone maps or small materialized aggregates of the two paper names. So I'm partly trying to name drop because I read database papers, but what I'm really trying to point out is that this thing actually has encoded, this file format has encoded in it best practices from the last 20 years of database research and implementation. So you'd be really hard pressed to do better, basically. That doesn't mean people aren't going to try. That doesn't mean you couldn't actually do better, but it would take a lot of work. So to give you a sense of one of the things that this type of organization allows you to do is you can do projection and filter pushdown. So what projection and filter pushdown basically means is that you have a filter, right? You only want a subset of the rows. Projection means you only want a subset of the columns. So what you do is you read the metadata footer. For example, in this case, maybe I had a query that only wanted column A, where the values of column C were greater than 25 or something. You look at the footer only, right? Not the whole 100 megabytes of file or whatever, just a little footer. And that will, and with some code, which is not easy to write, but it's also not particularly specific to your particular database, you can go figure out exactly which pages you need to look at and decode. So just looking a little bit of metadata, you immediately skip reading a huge amount of the work. Right? So that's how you query stuff quickly on Parquet. And this is not like Influx specific, right? Any query engine has, like Snowflake has a version of this, doesn't use Parquet, but it basically uses the same techniques. Any columnar engine will do this. And I think, so Parquet does it. So how do we use Parquet in InfluxDB 3.0? There's basically any persistent data that comes into the system is stored on Parquet on Object Store. And that, for anyone who's built a database in the last 3 years, that's kind of like a duh, right? Because that's the architecture. But that's a relatively new one. So in this case, what we have is we have a tier of things called the ingesters. They get data in this highly denormalized, like basically CSV type file format. They quickly go parse that, turn it into an in-memory format, which I'll talk about in a second. Spoiler alert, it's Arrow. And then it gets written into Parquet on some period, right? So it'll take the Arrow record batches, actually run it through the Parquet writer, which, what input it takes? It takes Arrow, right? So we're able to reuse the Parquet writer. My colleagues can go nuts optimizing it. And it all fits together. So basically data gets written to Parquet, and then when queries come in the other side, right, we have another, I was talking about the need to have a scalable system, so we have a second set of things that actually runs the queries that are called queryers. The query comes into that now fetches the relevant data from the object store and combines it with the data that's not yet persisted into object store from the ingesters, and it sends it back to the user, so at a high level. So like, where do we use Parquet? That is the persistence format. By the way, I think this is like, if you're building a database today, next 3 years, this is it. That's how it should be. Paul saw that 4 years ago. I only fully appreciate it maybe 2 years ago. All right, so now I'm going to talk about Arrow. Julian's already given my tithe, I hope. So I'm not going to put a thing in the jar, but I'm going to talk about it. So what do you get out of using Arrow? In my mind, it basically just encodes the best practice for doing columnar data memory, and I'll explain basically what it is in a second. So I actually don't think it's particularly innovative. No offense to anyone in the room. Like it was all described like a long time ago in both the database research literature, and it exists multiple times in multiple different systems. So basically any columnar engine that you've ever heard of, DuckDB, Photon, Snowflake, right? They all basically have the same thing. Vertica, if you've heard about Vertica. I mean, it's all basically the same thing. Because really there's not that many ways to represent a bunch of numbers in memory, which I'll describe. So the first thing that it benefits is you have the full type system, right? Like you have all the different sized integers and the floats and the timestamps and the dates and the struct fields, and like none of that stuff's particularly hard to do individually, but it's just a lot of work. Far more work probably than you'd like to imagine. So having it all just defined for you and not have to define the mapping and the data conversion from whatever format you have to this saves you a lot of time and effort, right? It has null support. If you ever implement a database, you'll understand why this is important. If you never have, I hope you don't have to worry about it, but like you don't want to have to retrofit this on after the fact. It also does like efficient encoding. So if it basically has the stuff that you're going to re-implement and rediscover as you try to do something like you have a lot of repeated strings, right? Well, I shouldn't repeat the strings in memory. I need some way to encode them, right? That's called dictionary encoding. It's been around for a while. Arrow just already has it. And then it's also got this natural integration point where you want to hook into other libraries. It's just like, it's very easy. Here's Arrow, it uses Arrow, you're done. The other thing that I don't think gets talked a lot about, but it's very important for databases, it's not really part of the Arrow spec, but it's part of most of the implementation libraries, is actually computing on the kernel is actually quite awkward to write fast kernels, which I'll talk about. And so using those optimized compute kernels and not having to re-implement them saves a bunch of time as well. Yeah, whatever. So I don't know, maybe you guys like memory, maybe not. So I figured I'd just like do a little example of what an array actually looks like in memory. So in this case, if you had 1K 8-byte integers, how does it look in RAM? It's going to look, if you sat down for 30 seconds and wanted to design how this is going to look, right, you'd probably come up with an array of 8K bytes that was all next to each other, aligned probably, so that the CPU would do a good job. And then you have then there'd be a validity mask, right? So in that case, this is marking which particular element is null or not null. You don't store that as a sentinel value in the array, because if you did that, then you have to do something if you ever want to store that value. So Arrow has this bitmap. Again, this is not overly amazing, but that's like the standard way to do it. It's kind of important, like, is it a null mask, is it a validity mask? In this case, it actually turns out that it's a 1 if it's valid, 0 if it's null. It could be reversed, that's fine. But what really matters is when you're going to talk to someone else, you agree on which one's null. So that's the basics. Like, there's other ones, but I just want to give you a flavor. Like, it's not magic. It's literally just like instituting best practice. This compute kernel thing, I don't know how many people know what compute kernels are or really care, but I'll try to tell you anyway. If, for example, you wanted to do an array and you're just trying to do something, you find where the value in one array is greater than the value in the other, right? That's all you want to do. The way you do this quickly on modern CPUs is you use, Julian was hinting at it, right? You basically want a fast vectorized loop, so you want to be using the hardware that's able to do multiple comparisons at the same time. And when I say you, I mean when you write if you want fast performance, this is part of why columnar execution engines are really fast, because they use this kind of technique. So you want to basically, like in single CPU instructions, you do multiple comparisons, and it goes down, right? And it figures out 1 where it's greater, 0 where it's not, and you have to deal with a little edge case. And so, like, I'm pretty sure any one of you in this room could figure out how to do this. Would take us probably different amounts of time, but it's not like whatever system you're building, it's not going to be special for, right? Like this should basically, doing this is like, it's not complicated, but it doesn't take 2 seconds either. And so, in this case, having a function that just does it for you saves you a huge amount of time re-implementing something that other people already did. And just to give you a sense of the magnitude, there's like 50 of these things because it's like less than, equal to, greater than, equal to, like less than a constant, right? Like there's a whole bunch of stuff that is like, if I enumerated it for you, it would get very boring, but you need it. That's the stuff you need to make a database really fast. And so having someone else having done that for you and obsessed over making these things quick is very time-saving. So where do we use Arrow? We use it all sorts of ways to connect things up, which I've already been hinting at. We also use it directly. So as the data comes in this highly denormalized format, right, the CSV file, we have our own parser that turns it into Arrow formatted record batches. And so in particular, in memory, it literally gets built up, and then over time, that memory will get snapshotted. The way Arrow is typically set up is not so that you are able to modify it in place. It's meant to be written once and then read a bunch of times. So we'll buffer up a bunch at some point, take a snapshot, and then all the queries and stuff will operate on those snapshots. And conveniently, the Parquet writer takes Arrow packages, right? So we just send the record batches off to the Parquet reader does its thing, and we never had to copy data, right? Went from input format, got turned into Arrow, then it goes to Parquet. The other thing that's very convenient now is like when we have our query engine, which I'll talk about a little bit more in a second, it also needs data, like the data that's not yet persisted in Parquet. So where does it get it? Well, it gets it from the ingester. Conveniently, the ingester already has the format, the data in Arrow array format. So we will just use the same format and send it back. So yes. Now, I got like three more major technologies. So we're going to cruise. DataFusion, I could like talk probably the whole day on this, but basically this is like, if you want to build a query engine, I've now done it twice. It's a lot of work, and you can do it. It's fun, but be prepared to hire a bunch of people for a while, and especially if you want all the buzzwords, like vectorized column and multi-core. If anyone cares what all this stuff means, I'm happy to tell you. But like, this is what you need for a fast OLAP engine. DuckDB has all this stuff, right? Like, you need this. It's got full SQL. I say full because realistically, no one should ever complain. If everyone ever claims to have full SQL support, they're lying to you, because there is no such thing as full SQL support, in my opinion. But it basically has like all the stuff that you would need. And it's also customizable, which we'll talk about, right? Like, Influx has both SQL, but also has a bunch of like time series specific stuff, both extensions to SQL, and then also our special language. So being able to not reinvent all the columnar vectorized execution engine, but being able to extend it pretty significantly was a major important piece. So what this basically, I always like to think in my architect hat on, what's the input and output diagrams? I'm sorry, there's too many inputs here. Basically, it gets a query in, it gets catalog information in, it gets the data as record batches, Arrow record batches. It does its whole thing in there. And then what comes out, you're probably being sick to hear, like it's basically just more Arrow, right? So the Arrow goes in, Arrow comes out, and it does all the stuff inside. All the stuff inside is this. Again, this is not meant to be like, we're gonna go quick. This is basically what you would typically find in basically any query engine. This is like the standard textbook sort of internal architecture, where you've got catalogs and you've got ways to get the query. You've got a couple of different representations of how the query is going to get executed in these logical plan trees or the relational operator trees. Some various transformations on it, and then the actual specialized operators. The point that's really cool about DataFusion, you can actually extend, and by the way, we use basically all these points in Influx. You can add your own data sources, you can add your own language, you can add your own internal optimizer, like plans and optimizer passes, both at the logical and physical level, and you can add your own specialized implementations. Right, so like you can customize it pretty good. So where do we use DataFusion? It actually turns out Influx takes, well, basically anytime data gets touched, other than the initial parsing and turned into record batches, it goes through a DataFusion plan. So we have a couple of different front ends. We obviously use the SQL planner that comes with DataFusion. We also have our own implementation of a language called InfluxQL, which is a domain-specific query language for time series, but it also compiles down to a logical plan and then gets run through the DataFusion machinery, which I'll talk about. Also, when we do compactions or we do, when we do the actual initial writing of Parquet, that all goes through DataFusion plans as well. And then we have yet another way to run queries that I won't go into. It's called the storage gRPC. That also makes a DataFusion logical plan. So basically, they all make DataFusion logical plans and then all get run through the same set of operators. What this lets us do now is as we go geek out, or I go geek out on the weekends, right, and make DataFusion obsessed about some particular area of DataFusion performance, it all just flows back entirely to Influx, or other people do it. So, and then what comes out is record batches, and then depending on where it's going, it'll get sent to different other systems. Right, so that's basically how we use DataFusion. All right, Arrow Flight. Here we go. So, I know we're on a world tour. I got two more, Arrow Flight and Arrow Flight SQL, if you're paying attention. So Flight, I'm also guilty of implementing in the past life how to send data over the network. But basically, like if you're a database system, especially if you're a distributed one, right, you need somehow to take the data during query processing or during storage or something. You just send it over the network. So you can either invent your own protocol and do it, or you can use a pre-existing one, right? Obviously, we chose to use Flight, and the reason is because it takes Arrow, so you don't have to copy it, so you get efficient network transfer. The other thing is you then don't have to have a giant team, giant being more than 0, of people working on clients, and writing client libraries and managing them and testing them and stuff. Which it adds very little business value, but it's required. You have to have it, but there's nothing time series specific about it. So if we can avoid implementing them, all the better. So when I say it's network efficient, it retains the same. In some ways, it basically just takes arrow arrays and stuffs it over the network. It's more complicated than that, but that's like the high level idea. So it's not like rocket science, but having all the infrastructure in place just cuts out a huge amount of the redundant implementation. It's CPU efficient, so it's 0 copy. I put 0 copies in quotes because depending on how pedantic you are, maybe it copies into the kernel network buffers or whatever. We have certain people on my engineering team that are a little more focused on this, but basically, you certainly don't have to do a lot of computational transformations before you send it and receive it. So it's very CPU efficient. We've never seen it show up on our traces. And then also, as I was hinting at, you get access to all the pre-existing clients, right? Like the InfluxDB 3.0 Python client is basically 100 lines of Python code because it just wraps the Arrow client, which does all the actual work. And the same thing for Rust, and the same thing for Go or whatever. So, we had a whole team that was focused on the clients at Vertica when I did that. So specifically, we actually use Flight in two major pieces. First one is the native query protocol, which I just hinted at, right? When you run a query against Influx DB 3.0, it actually comes in as Flight, comes in as Flight SQL actually. Well, it can come in as Flight SQL. I'll talk about that in a second. The native protocol just uses Flight. The query comes in as like the payload. The query then goes and talks to the ingester, gets the data, and combines the response back and sends it back to the client, also as Flight, right? So the client, both the input and output come in as Arrow. The other thing that I think is really cool is that internally, right, I've been like glossing over the connection between the query and the ingester, but it's very important for the time series database to be able to return, as I mentioned before, data that's not yet persisted to Parquet, right? So the stuff that's in memory in the ingester. So when the query comes in, you need to combine it. So you need to basically get the ingester to send you the not yet persisted data, and you'll probably guess, right, what that uses, right? It uses Flight. And this actually let us get it going very fast when we got it working good. It actually turns out another beauty of building systems like this is that we used Flight initially. It's great, but it actually has several additional sort of, there's ways we could make it lower latency. It's basically the long answer. But we got going with Flight. That was good. And then as our business needs evolved and engineering capacity freed up, we then went back and spent some time focusing on building a more specialized version of that protocol. Actually happens to also basically be built on Arrow, and it's kind of a bastardization of Flight, but my point is we could focus that engineering effort later when we found it was actually important rather than having to do it up front initially. All right. Oh, yeah. So finally, I think I'm going to make it in time. Flight SQL. And I'm going to show you what we do, and then I'm going to offer a cautionary tale about some other things that you might be tempted to do if you were building a database these days and age that want to talk SQL. So the real reason you want something like Flight SQL is to get access to the ecosystem of SQL tools. Well, all right, I guess I talked too much. I'll explain what that means. So you just, if you have to, as a database vendor, go do the integrations, like that's a huge, huge amount of effort. You want to not have to do that if you can, and that's where Flight SQL really helps. At a high level, what Flight is Flight is a protocol that's built on top of, or Flight SQL is a protocol that's built on top of Arrow itself. And it adds not just the ability to send data back and forth as record batches, but you need to also now interface with the existing clients in the ecosystem. So the way typical software is designed, right, that talks to databases, you probably all have experienced this perhaps as programmers, is that you don't directly typically use a client for the database system you're talking to. You almost always implement your system in terms of something like JDBC or ODBC, although I know that makes me sound old because those are like the older versions of things, but every programming language will have basically their database access layer. And then typically what will happen is you as a database vendor have to go implement that database access layer for your particular protocol. So if you want to do that, again, we had a team at Vertica that did that. It's actually quite non-trivial to implement all those libraries, not just because there's so many of them, right? Because people like whatever their native clients are, but it also the translating from like whatever the Java data types are in JDBC to whatever your native data types are is a non-trivial amount of code. Now I posted that basic content on LinkedIn sometime, and some guy from Wall Street told me, I don't know, it's actually fine. It's like it only takes 1,000 lines to implement JDBC, and he pointed me at some repo from some financial thing, but like all the variables were like one letter long, and there was no tests, and it was like, every statement was like jammed on there, and he offered that as an example of how it was easy to implement JDBC. So anyway, I will respectfully agree to disagree, and not having to implement JDBC is a good thing. So that's basically the benefit you got of Flight SQL. So in fact, we don't have a JDBC driver. We use the JDBC Flight SQL driver, and it's awesome. The final piece, I think I have a few moments left, but I don't have my slides. That's too bad. I'll tell you just in words. A very common thing to do when you're building a database and you don't want to build JDBC drivers, which no one does, is to try to hijack the Postgres protocol, right? So very, very common thing to do is like, oh yeah, here we go. All right, I'm back. Good, I can show you my pictures. All right, here we go, we'll skip this, because I've already talked about all this stuff. Yeah. All right, this is the JDBC. So I just want to show you what you probably are tempted to do when you're faced with this problem, and I want to convince you not to use Postgres, but to use Flight instead. And I'll show you why. So, because we did the first version of InfluxDB 3.0, we use Postgres. So this is basically what people, I think, oftentimes will do, because Postgres has a big ecosystem of existing JDBC, ODBC drivers, integrations basically anywhere. So the very first thing you're probably tempted to do is you'll translate whatever your server generates. Oh, I was too aggressive. Here we go. Oh, it's going forward. Back? No? Well, anyway, so what you do in Postgres, what you do is you'll translate your internal database format into Postgres, the Postgres wire protocol, which is called Phoebe, typically front and back end protocol, because it wasn't actually designed to be a general purpose protocol. It's just what they happen to call it. And then, as long as you can, and it's a very simple protocol. It's actually very inefficient. Among other things, it's text, yes, it's a binary one, but it's a row-based format, so you have to pivot it if you're a column store. So it's computationally inefficient, which is bad, but hey, you've got the access to the ecosystem, everything's good, right? Well, it turns out everything's not good, because the very first thing the Postgres driver will do, that you'll find out, is not just the actual shipping bytes across the network, is that the first thing it'll do is make a bunch of SQL calls to the Postgres metadata tables on the back end. So you not only have to implement this protocol translation layer, you also now have to implement some version of like PG meta, whatever tables. So this is great. You can do this demoware like 80% of the work rate, but actually making this work for real is very, very, don't do it. It's my recommendation. Use Flight SQL. So I'm basically out of time. So basically this was great. It works far better than I ever could have hoped. If you want to build another one, I know a bunch of technologies. I'll be happy to tell you all about them. So thank you.